present once again is electrochemical exfoliation of graphene oxide for use in concrete products. This was an experimental research project that was done back in 2019 when the laboratories were open without any hesitation. But as you also know, there is a long way from lab to the real world marketplace, although the results might be promising. I'll start by briefing on graphene and its properties, then we'll move on to explaining why do we need this concrete product. I'll then share the laboratory experimentation and the results. My email address is, as you can see on your screen, and I will be more than happy to respond to any of your inquiries, suggestions, collaboration proposals, especially, and also other things that might come in your mind. The first question that I have to explain a bit is what is basically graphene? That is a one-layer thick structure of carbon atoms that has some exceptional crystalline quality in the nanoscale. It has recorded high thermal conductivity, which is beneficiary to the curing process as well. As you might already know, the cement hydration reaction is exothermic by nature, which means it generates heat as the chemical reaction develops. Endothermic reactions, on the other hand, require heat absorption for development, and that's just for a recap. Now, this high thermal conductivity of graphene particles help in cooling down the inner parts of the concrete blocks, especially in the first 3 days when the strength gain occurs. Once the internal heat finds its way outside of the concrete block, the chances of cracking reduces by a lot. In fact, in the traditional curing processes, we spray water on the surface to cool down the block. Relevant literature had reported up to 30% improvement in the compressive strength of concrete reinforced with graphene particles due to the better internal curing process. The next most important question that you might also ask yourself is that why we should put a such an expensive material in graphene, in concrete. It is expensive, and by the way, just so you know, each gram of high quality graphene is priced around $500, and you're going to need 3% addition by the mass of cement for an optimum result. I did a math for you. For each ton of concrete, you will need 10 kilos of graphene. And if you decide to reinforce your concrete with these nanoparticles, that adds up to $5 million for only 1 ton of concrete. And with a 1 ton of concrete, it can only pour a small slab. So it is by no means any viable financial consideration. Nobody does that in a commercial scale, unless stupid, maybe if. But apart from the unviable cost of reinforcing concrete, let me emphasize here more again, with high quality graphene, apart from that, you can think of mechanical improvements and the prospects. We can think about affordability later on in this presentation. And we've actually made some low quality graphene oxide in the lab for a price almost 20 times less. And it can be reduced even further upon commercialization and optimizing the processes involved. So another mechanical benefit is the high electrical conductivity of graphene. And when I'm referring to another mechanical strength, I'm talking about another benefit rather than that curing that I've explained previously. It is indeed being categorized as a superconductor. Now, you might say that this is a destructive property for concrete as it scales the rate of corrosion. And that's a perfect argument that we don't have an investigated answer to. However, thinking of polymer coating of steel reinforcement, doesn't look irrational. The major advantage of highly conductive concrete appears when you think about the future roads that can charge your electric vehicles on the go, which is a prospect, even if you look at the state government plans. There have been some initial studies done in Sweden on this topic too. Moving on, we must consider what are the downfalls and what prevents us from getting there. If you get through the existing literature and summarize the outcomes of the several past years, you will end up with a list of problems like this that you can see on your screen that prevents us from further developing the promising graphene reinforced concrete. We've already discussed the first two problems are being costly and the lack of studies around the corrosion rate. Another problem with graphene when it comes to mixing in concrete returns to its hydrophobic characteristics. It just doesn't like to be mixed in water, which causes agglomeration, meaning that you will be seeing chunks of little black balls in concrete. And it's not good because you are expecting a continuous path for both electrical and thermal conductivity and not seeing chunks of black balls. But remember, we have so far talked about graphene and not graphene oxide. Luckily, there is a much cheaper way of producing a material really similar to graphene that is called graphene oxide. Graphene oxide shares a lot of similarities with graphene, such as high compressive strength and both high electrical and thermal conductivity. Then, in contrary, however, it is not hydrophobic, and I mean graphene oxide. Rather, it is hydrophilic, actually, because of the oxygen atoms, which means that it not only doesn't create chunks of little black balls, it actually helps in a better dispersion. That continuous path for electrical and thermal conductivity can be achieved by using graphene oxide instead of graphene in concrete. From the comparison between the molecular structure of graphene, as you can see, you can tell that it yields a relatively lower thermal and electrical conductivity than pure graphene because of the impurities that are embedded in its structure, which is both good and bad. It appears to be good for a lower corrosion rate and bad for the conductivity matters. Nevertheless, the major advantage of reinforcing concrete with graphene oxide and not graphene is the affordability of this material, because after reviewing the literature, there has been no significant difference observed between these two in terms of mechanical performance in concrete. So basically, by using graphene oxide instead of graphene, you can save a lot and get the same outcomes from the mechanical perspective. So there are two main methods of producing graphene particles, which I will explain in this table. The first cheaper method that is being used to produce graphene oxide is faster in comparison to the other one. This is the method that we have actually used during the laboratory experiments. The second method is used to produce high quality graphene, which has applications in other industries such as electronics. That's just super expensive. It's not going to be viable by any means for construction application. Electrochemical exfoliation, the options that we've chosen, refers to the process during which the graphite sheets are oxidized in an electrolyte followed by an ultrasonication. Hydrobromic, hydrochloric, and nitric acid plus sulfuric acids are typically used as electrolytes from which sulfuric acid is proven to perform in highest efficiency amongst other acids. So we used sulfuric acid for that reason in our studies. In the beginning of the process, we have lowered the concentration of acid to 2% in this study for exfoliation and also for the safety matters. Starting off with a low voltage for a few minutes from the beginning of the electrolysis would allow the graphite to wet and prepare for proper exfoliation. The voltage applied could be ramped up after a while to speed up the process. The electrochemical exfoliation of the graphite sheets usually yields thick layers of graphene with a small surface areas. However, the modification of the acidity of the electrolyte and the voltage applied can enhance the quality of the final product. I don't know if I'm running out of time. I guess I have 4 more minutes, so I have to speed up. Cathodic exfoliation refers to the process where positive terminal from the battery is connected to the graphite. We have tried this method first, and there was no sign of exfoliation observed after 24 hours with a 6-volt DC current. Even 12 volts input didn't help the process. The reason being probably the sizes of ions in the solution. Once the current is applied to the exfoliation bath, sulfuric acid decomposes into two major ions. That is 2 hydrogen and 1 sulfur. This means that in the cathodic process, we've been mistakenly forcing the large ion, which is sulfur, to get between the layers rather than pushing hydrogen, the smaller ion, inside the layers of the graphite. Whereas the more rational way was to force hydrogen to penetrate between the layers. So we have corrected our mistake and switched the positive and negative electrodes. In addition to that, we have tried to test a looser stick with a lower density of 2,540 kilogram per cubic meter. We applied 12 volts DC current again, and this stick had completely exfoliated into graphene oxide after 24 hours. The next step was to excel the quality of acquired GO, that is graphene oxide, via the means of ultrasonication. An ultrasonicator is the apparatus, so that the picture that you see on the left-hand side is exfoliation bath. If we use anodic exfoliation, which means that connecting the negative electrode to the graphite stick, this is the practical way of exfoliating graphene oxide. And the other bath, we had 2 baths in our experiment. The other one was the ultrasonication bath. And an ultrasonicator is an apparatus which shakes the solid particles in liquid solutions using high frequency vibration. Using that, it helped us collecting much finer particles after the filtration. Since we are dealing with nanoparticles in this study, it was important to consider the right choice for the filtration process. The most frustrating step indeed was filtration, as it took the most amount of time in the whole experiment, 3 days until dry particles were ready to collect. So that being said, it opens an opportunity for future studies. And the question that runs that study is to be, what is a better filtration process to speed up the production process rather than spending 3 days to collect dry particles. At the end of the production process, we have managed to make 60 grams of this valuable product available for public purchase. Within the first few weeks that it had become available, we sold 10 grams online to one of our customers through the innovation store. It somehow shows the existing demand in the market. Of course, we are not near to the full-scale commercialization scale by any means, but if you look at the market price and the number of studies done in this area, you can get an estimate about the possible return on investment in case you decide so. The product is recommended to be used only for research and development purposes, as there are still so many areas subject to more investigation. Some of those gray areas that can be noted at this stage are: number one, the quality of the product to be assessed by an scanning electron microscope, or SEM in short. This way we can outline which stage of the production requires more optimization. The number two of that gray list is the process that takes less time to complete. As mentioned, the current process takes 4 days for 60 grams of the final product, which is not ideal. And to wrap up the gray list, we need a proper market evaluation to be done before commercialization starts, i.e. how many customers are thriving to use graphene oxide in their concrete products. And another question that we have to ask ourselves is, does it need government support, or can it be done by a private entity? And of course, many more questions that can come into your mind. Moving on, the concrete mix design. In the next phase of the study, we had made cement mortar samples for the electrical resistivity test. The electrical resistivity test had been chosen mainly to outline how good the product is for roadworks. Remember, the future roads are capable of charging electric vehicles on the way. So this table shows the mix design. Graphene oxide had been added to the mix with the ratios of 1%, 3%, and 5% by the mass of cement. We have tried to keep the water to cement ratio constant as 1 to 3. A quick recap is that a lower water to cement ratio directly enhances the compressive strength of concrete, which is always a priority for contractors and builders. The mixing process had been done in accordance with the Australian Standard Code. Cement and graphene nanoparticles had been mixed first, and water was added slowly in the mixer. The mortar had been mixed for 5 minutes, and 4 different samples were obtained at the end, as you can see right here. To get rid of the air bubbles once poured in the mold, the samples had been vibrated for 1 minute and left in a water tank for curing after 24 hours for a duration of 3 days. Another interesting possible area for future studies actually return to this very stage, that is curing, as we are expecting better performance even without curing. But in this study, in order to stay in the safe zone and to avoid any further uncertainties, we managed to comply with the standard codes, especially when it comes to curing. So here are the results. As expected, the samples with a higher portion of graphene oxide recorded a higher electrical conductivity, or in this case, lower resistivity. However, it is not rational to increase the portion of graphene in the mix due to many reasons, the most obvious one being the cost, and the second reason that comes to mind is the uncertainties around the corrosion rate. Regardless, being able to produce graphene oxide is being considered as a technological advancement for the material industry. This was a full summary of what we have done during the past scientific experiment, and I hope that you have taken at least 1 point for your future research studies too. I'll also be more than happy to discuss the future collaboration opportunities with you. My email address for this reason is farid.sartipi@iconsmart.com.au, and that was it, yours. Thank you. If there are any questions, I'll be more than happy to answer.
Thank you for that, Farid. I have a question. If anyone else has a question, feel free to raise your hand. I've already started the Q&A session. You can unmute and start your video if you like. My question is that I'm surprised there isn't currently any sort of like industrial scale production of graphene oxide. Is it not used in like other industries, or is it just too new a material? Sorry.
What was the last part of your question?
I was just wondering, is it not currently used in other industries, or is it just like a research tool at the moment?
In Australia, we've got one mass production factory that is in Western Australia, actually in Perth. But the market in New South Wales, Queensland, Victoria, and South Australia is actually thirsty. So I reckon that's a huge opportunity for anyone who wants to invest in this material. And in terms of other industries that had adopted the production of graphene oxide or graphene, I guess electronic industries, mainly because of its superconductivity. So yeah.
Thank you. That makes a lot of sense, actually. But yeah, great investment opportunity. I think Isaac has a question.
Yeah, Isaac.
My question is that how did you capture, or how are you going to capture the cost of this whole thing that you and
With bloods and but
the expenses?
the
How
costs of how big are we talking about? If it's still in the laboratory scale, it is not an expensive process to make 60 grams. Like it costs around 400, 500. It was 2000. I can't remember exactly.
okay.
But you can sell each gram for, so that covers the costs of production actually pretty much. As for the laboratory scale, of course, if you move on to the commercial scale, the cost will be lower, the returns will be higher. So, yeah.
Okay. Thank you. Makes sense. Thanks.
Cheers.